So we're looking at factors that will increase the speed of reaction. I can show two of them with this simulation. You've kind of already seen one of them with the simulation. So I'm going to start off again with three of the ABs. Sorry, three of the A's. 1, 2, 3. And then three of the BCs. Remember that when you have the yellow floating around, that's their unreacted species. So I'm going to begin the experiment. And we already talked about how, like, if you don't have enough energy to begin with, then your collisions, like, nothing's going to happen. So I'm going to raise this up. And what I'm trying to do is catch it so that it's just like a little bit close. And what I'm trying to do is at least get like one to go. I might have to give it just, oh, there we go. So I was close. I was able to get one of them to go at that speed. I meant to say at that temperature, which is speed, like they're moving faster. So you might be like, how did that one do it? Well, you notice that these aren't all going the same speed. So what this is measuring is the average energy, or like kind of like the average speed, the average temperature. So it could be that one of them bumps another at an angle where it's actually moves faster and some of them are moving slower. So overall, you can sometimes have like one little molecule just barely get up enough speed to get a reaction before getting over the total energy. But there's no way we're going to be able to get the whole system to go without having a little bit more energy in it. So I'm going to try to get it right there, barely over. And hopefully what we will see, there we go, we had another one go. Now let's see, it may be too wild and it may start going backwards. But what happens if I put the energy really, really high? I don't know, sometimes this simulation won't actually let all three of them go, but let's see if it might possibly go. Let's see, are you gonna happen? Waiting for it to bounce off of it. It's getting close, go on. Oh man, yeah, so this simulation will send it backwards because it's also showing a reversible reaction all at the same time. So in just a second, it should rejoin. There you go. Now we're rejoined. So a lot of times this simulation won't go all the way with just this number of balls in it. So that's one thing, though. You can see that increase in the temperature did allow more of them to join. Here's the other thing that you can do. I'm going to reset it all. And instead of starting with 3, I'm going to start with 10 and 10. So what I've done is I've increased the concentration. What that's going to allow is more collision and more energy transfer with more collisions. So we're going to begin that experiment. So look how many more are in there. Notice that green line in the graph in the center, and we are not high enough energy for anything to happen. So I do need to get my energy up. But this reaction should happen faster. I should have a lot less yellow balls really soon because, look, I've already got 2 or 3 joined up. Because I've just got more possible collisions that's going to run into. More possibilities that we can get more things joined up. Now it looks like, I don't know, I'm stuck at like 2 or 3. 3, I'm seeing 3. Maybe 4. See, it's moving so fast it's hard to keep up with it. But definitely, I mean, I have like 5 now. So you can kind of see that I've got just lots more collisions. So that's what concentration does for you. It just gives you a lot more collisions to work with, which the more collisions, the more likely one of those collisions will be of the right orientation. And so you're going to have a faster reaction.